Welcome everybody, and thanks for listening for my talks. This is a talk I gave a few years back at OzSecCon in Netherlands. So I like recycling, so we save a few electrons here. During the talk you can take photos, you can ask questions, just raise your hand. I'm sure I'm not explaining everything properly, so there might be some issues always rising, especially if you don't know about safe locks. But that's what the talk is about. I'm trying to give a little introduction to manipulation of mechanical safe locks. And this is the short version. Basically, tell all the basic properties of a normal safe lock, such as this. You can play with this. If you see this somewhere, you can play with it. There's some measuring equipment attached to it, but don't care about that. And you can ask me questions about it. We're gonna go through some of the properties in those locks, why manipulation actually works, what kind of shortcut we can use, and I'll show some actual measurements of locks to show just how small things are we measuring through the dial to make it possible. And who am I? Well, I'm Jaakko Fagerlund, as you already saw. I'm not an old guy, but young, at the heart at least. And yes, I'm a tool and die maker. That's my usual day job. In the nighttime and weekends I crack safes for money, legally. And yes, I have heard all the jokes from day one. And I prefer doing non-destructive entry, so manipulation, lock picking, whatever, you name it, I do it. If I don't have the tool, I make it. That's the beauty of my profession, I can do stuff. I have a personal interest in electronics, coding, breaking things, taking apart, figuring out things, hacking, whatever. If it's something that has a moving part, I'm interested in it. So, how do you get a lock open? Well, this is the very easy version. You have the code for a lock. So the lock opens with the correct numbers. In this case, a mechanical combination lock has 3 numbers usually that you need to input to get the lock open. And what it does is it aligns gates in the little wheels in the lock. And when they're all aligned, it allows a little fence to drop in and release the mechanism to turn the slide open. But here comes the first clue of things are not perfect in this world. The wheels in the lock are not the same because they're manufactured, there's tolerances, they're always crooked some way, they're not round or whatever. It just doesn't work perfectly, so there's a little anomaly that we can measure from the lock. We don't know how much difference there is between the wheels, but we can do relative measurements against the lock itself. And unfortunately, because this is not my laptop, there's some problem with the images. They don't show up. But anybody who wants a copy of this on a PDF format can get one. It shows nice pictures. It should be showing a nice picture of the lock's cam. Behind here is a little wheel called cam wheel, and the fence, which is looks like a seahorse. It's the part of the lock that we use in manipulation to figure out if we are correct or not. And just to give a little insight into the correct or not, it's not so black and white. When you're manipulating a lock, you are always more correct than previously. It's only correct when the lock opens. Up until then, you're just more correct. It's a iterative process, basically. Again with the pictures. But anyway, when you dial some number on the combination wheels and the little fence in the lock is resting on the wheels, there's a spring pushing it against the wheels, you can rotate the dial to feel 2 contact points. And of course, because the dial has nice numbering on it, you can use those numbers as a reference point and see at which points at which numbers those 2 contact points occur. And you measure the distance between those points. And if you dial some combination and measure, I have 5-number large gap now in the contact points, then you dial a bit different number, like change one wheel to another number and test the contact points again. Now you have 4.8. So now you know you got closer, you got better reading. So whatever you dialed is more correct than the previous one. And of course, if you only move one wheel, you're removing all the other variables in the lock. And basically, it's telling you that that particular wheel is now more correct. So you're looking for very, very small changes in the wheel numbering. Usually it's like quarter of a number, so it requires very good eyesight when manipulating and making your notes. Again, doesn't show up. There should be a nice little graph here showing what does it look like when a lock is crafted. Basically, you turn all the wheels at the same time when you start out. And for example, turn all wheels to, like, for example, to 20 and go check your contact points and record the readings on a graph paper saying at 20 we have left point here and right point here. Then you rotate to 22.5, again, note the readings, then 25 and so on. So you get a nice little line graph of 2 lines which tell you about the shape of the wheels or the whole wheel pack. You don't know how much the differences will be, but all the little differences show up. And if you find in those readings that they get more closer, like I mentioned, if you get smaller contact point area, it means that might be the correct number. On a graph, you have 2 lines basically converging with each other or going closer to each other. So you know that that's a possible number. You don't know which wheel it is. You just know that that's a number. You can test it afterwards to see which wheel it is, or if you only moved one wheel, you know that that's the correct number for that wheel, or at least more correct. If you then have one number known and you have a 3-wheel lock, you need 2 numbers to get the lock open. At that point, basically, you have to do another run. When you know something, you turn the wheels that you don't know to something new and turn the one wheel that you already know to the one number that you just discovered. You're basically parking the wheel. Yeah, that I already went through. Yeah, there's the parking is basically you keep one wheel fixed at the number you found. So you remove that variable, and basically that wheel is not in play anymore. It doesn't contact the fence because it's probably correct now, or at least more correct. So the fence should be resting on the other unknown wheels, and you can then do the same manipulation graphing procedure for those two wheels to find something new. It's very simple as an idea, very, very hard to actually learn and do, especially get your head around it. Like, how many actually know how to dial a mechanical combination lock? Raise your hand. So roughly 1/3. So that gives you an idea of how, if I continue with the questions like, do you know which way to turn the wheels? Do you know how to dial 4 wheels? We get less and less hands until we get to the safecrackers. So, yeah, it's a process, very easy to understand with the lock when somebody is actually showing you and you can play with it. But yeah, and just one from everybody. I'm just laying my weekend here. So, but yeah, the reasons why this manipulation thing works relate to mechanics and mechanical tolerances. I stole a picture from a book that I own relating to machining. It shows typical tolerancing images of flatness, straightness, position, whatever. Basically things that are telling you the world is not perfect. So everything has to function together. When you're making mechanical parts, you make a nut and a screw. They have to screw into each other, so the nut has to be larger than the threads on the screw, otherwise it won't work. How much larger? Well, that depends what you're trying to achieve. For example, the problem might be temperatures. Like in a lock we have steel parts, we have brass parts. Brass expands more with temperature than steel, like 3 times. So, for example, if I start heating that lock, it doesn't work anymore, probably. So that's one consideration for tolerancing parts. And for example, when you're talking about manufacturing a product that is made by the millions every year, or thousands of parts, you run into the problem of how to tolerance parts so that whatever you take from the bin when you're assembling it, it has to function together with the other parts. So there's always a variance. If you drill a hole, it might not be straight, it might not be exactly the same as the other one. So you give tolerances for everything, like you make the hole large enough so it fits always. And all the different machining processes, manufacturing processes always have the tolerances into the parts. And this makes it possible to have a lock that works every time. Just like with a pin tamper lock, you have the pins are smaller than the holes they are in, so they move. But of course, because the tolerances allow it, the pins might get jammed easily, or they do not, for example, in a pin tamper lock, they don't bind at the same time, even though on paper it should do that. So we're basically in a safe lock. We have uneven forces. Like, for example, the fence has a spring which is on the other side of the fence, so it's not pushing it straight down, it's actually trying to lever it away from the wheels. So, of course, if you have a wheel pack that is from the side like this, and you have a fence coming down to it, it should contact all the wheels at the same time, but because the spring is pushing the fence like this, it's only contacting the one wheel at the corner. So that's one advantage that we can use. We know that, like, generally speaking, 80% of the cases that one wheel, the wheel number 3, the last wheel of the combination, will be the first one to tell you its number when you're manipulating it. After that, you get the second wheel and finally the first wheel. And that's one of the little shortcuts we can use. The other one is basically what I referred to earlier, that the wheels are not round. Technically they are round. I actually did some measuring from that particular lock with a small measuring tool at work. And this is the graph around it. This is basically numbered from 1 to 95. The gap is 5 numbers wide, so it's not included in the measurements, but it's showing just how small differences we are talking about in the non-roundness or out of roundness condition. We have basically 0.2 millimeter differences in the wheel, like something you can't see but you can measure. And this graph is looking a lot like a sine wave. It tells me that the wheel is actually round or round-ish, but it's offset from its center hole. So the outside of the wheel is not concentric with the actual rotation axis. So it depends on the position of the wheel when you're turning it. It might appear larger or smaller compared to the fence of the lock that you use to measure against. Yes?
Can you just explain the x-axis? So is that a difference in radius from a nominal diameter?
The x-axis is basically when you have a dial like this, it's divided into 100 numbers.
Oh, I'm sorry, the other.
The y-axis. It's radius. Difference in radius. Yeah.
The nominal diameter.
Yeah.
The nominal radius. Okay.
So it's very, very small. And it's showing that it's round-ish. We can always make everything perfect, and it sure is perfect until you use it once, and it's not perfect anymore. Everything wears down over time. Then I did another measurement from another lock, this time a Lagarde. I don't have it with me, but it was showing basically the same thing, kind of sine wave shape, telling again that we have round-ish wheel, but it's again offset from the center of rotation. This time a lot larger, 0.5 millimeters was the largest difference. And it's showing some sort of spike, as you can see. I'm pretty sure there's a manufacturing process that makes a little divot in the wheel that shows up in the measurements. But again, almost round wheel. And this is the problem of how do you make parts that work together just enough so it doesn't get out of hand with the price of the product. Like, sure, you can make everything just perfect and ideal and everything just works and it's unpickable and whatever, but it works just once, and it costs 2 million per lock. So, yeah, you can do it, but there's no point. You can do it cheaply. You can do it good enough for most people or most applications, and also cheaply. Like, for example, that lock on the table costs, what, 50, 60 euros or dollars, or whatever the currency is. It's always the same. And of course, you have to build it to a price point. Otherwise, people don't buy it. They always want something cheaper. Like, for example, when I was the first time in the USA, I discovered in the hardware store that you can actually buy your house locks for $10 or something like this. Holly probably can say more about the prices of hardware, but I got the suspicion that, yeah, there's a reason why people want cheap things. They don't want to buy anything more than enough. If it locks the door, it works. Same with the combination locks. You can spend 50, 60 euros and buy a lock that works, and like the show of hands told me, almost nobody knows how to open these locks even with the correct numbers. So maybe that's security. If you don't know how to operate it, it's secure. No, I mean, sure, you can buy also the very expensive models that cost 2-3 times this and are manipulation proof. Well, proof. They always have a way of opening them. Yeah, it's a balancing act basically on what do you need to lock with that particular lock, and who are you protecting against. Like, for example, you can have that sort of lock on a filing cabinet behind locked doors and you're probably good. There's alarm systems, everything, and you can not expect to see anybody there with 1 hour of time and a laptop and a bunch of software to break that lock. Or a guy with a graphene paper spending time and money, and then they open the safe and notice that it's empty. Not that I've done it. Don't worry, it was not my safe, and I got paid for it. But yeah, here's a short summary basically of these shortcuts we can use. The dialing tolerance is a thing that comes from the lock specifications. Like, for example, this lock on the table is the SNG 6730, which is the most common safe lock you can probably buy or come across. And it has a dialing tolerance of roughly plus minus number. I don't remember the exact tolerance, but it's roughly, you can be a number off when you're dialing and it still opens. What it means to a manipulation, it means you only have to test every other number. So originally that is technically 1 million different combinations, except the last number can't be between 90 and 10, so that's a 20% reduction of numbers straight away. Then you only have to dial every other number, so that's only 500,000. And there's a lot of other little things that you can use to cut down the number down, basically to a point that you only have to do a linear search of the whole wheel pack instead of exponential numbers. Like, sure, it has 3 wheels, so 100 times 100 times 100 becomes more like 100 plus 100 plus 100. And of course, when I mentioned measuring, and the only measuring tool you have on a safe that is in front of you is the little wheel with the 100 numbers on it. And you have to read it with your own eyes. Like, you have to decide if the number is just correct or if it's like half a number off or 1/10 of a number off this way or that way. But then becomes the human problems, like if you shift your head a little, you had two lines pointing at each other, but if you shift your head, they're not pointing at each other anymore, so you get little parallax errors. And when you're trying to measure something that is 1/10 of a number, you get in trouble really fast. And of course, bad eyesight, poor lighting, everything always works against you. But electronics, they're cheap. Here's an example. You can play with it later once I get it hooked up to a computer. I purchased on eBay a rotary encoder, basically a very handy measuring tool for angles. It divides the 100 number dial to basically a 4,000 number dial. So it's much more accurate than human can ever perceive with the eyes. So it removes all the eyesight problems. It gives you all the numbers onto the computer, and you can make software that records all the readings for you. So you don't have to mark everything on a piece of paper. And of course, with computers, you can always just save your progress and continue later. Unlike with when you're manually doing something and you don't necessarily even graph onto a paper, like you're doing just mental image manipulation or freehand manipulation. If you don't get it open, then what? You have to start over basically, because you don't have anything saved on paper or on computer, nothing. With a computer or paper, you can always get back to your measurements and see where did I go wrong. So basically, that sort of measuring tool is a start to a little advanced exploits, like using those sine waves, like I showed you, that the wheels, when you're doing accurate measurements, they show up like sine waves. But if you have 3 wheels in a lock, and of course they are not synced, so you basically have 3 sine waves or sine wave shapes on top of each other when you're measuring them. You can basically do a software-based attack and measure the lock once around, like do 10 or 20 readings around it, and slap 3 sine waves on it, and it basically tells you exactly what the correct numbers are for the lock, all the 3 numbers at once. But you only have to dial 6 times to figure out which is the correct order for those numbers. And the ultimate manipulation tool is the soft drill, which is basically a robot that does the exact same thing as a human, except in 15 minutes. Well, a human might take an hour, 2 hours, and even longer if you have to restart or you make an error at some point. Machines are nice, they don't take breaks, they don't need cigarettes or coffee, especially lunch breaks. They just work. The other option is to have a normal dialer which just brute forces the lock and basically tries every combination until it opens or not. And believe me, 50% of the cases it does not open. There's some problem that would come up when you're dialing manually, but not with a machine. The machine is stupid, it doesn't know anything. It does exactly what you want or what you told it to do. So yeah, so that's again showing bad images. I had a couple of open safes. You can actually see on the left, open Caso safe. It has a weird handle that opens upwards. I don't know the reason. Maybe to deter thieves because they try to open it downwards and it doesn't move. But yeah, that's the story of manipulating a lock. Badly presented, and yes, I've not been sleeping well. I arrived yesterday, so I'm blaming everything else. The problem is not me. Yeah, thank you. And if you want a copy of this on a PDF, come talk to me later. I can email, send a WhatsApp, whatever, stuff. Thank you. Okay. Let's see. I can actually show that one if it shows up. That's when I was mentioning about measuring with the sine waves. I can show this on my laptop because it actually works there. But all those little blue dots are one measurement. Every 5 numbers, I did a relative measurement from that with the electronic tool to give relative readings. And as you can follow the little dots, it's kind of showing us a sine wave, except not in all the places. And it's not in view, but around 85 somewhere here. It should be going like this, like a sine wave, but suddenly there's a drop. The dot is somewhere here. That's one correct number in the log. The other is somewhere around here. Again, missing the dot. It's somewhere down here. So this is my first attempt at the sine wave attack, or whatever you want to call it. But it basically works. It just needs some fine-tuning. And I'm not a computer expert, so I just punch numbers until it works. Yeah?
So, I'm a little bit unclear. What are you actually measuring from the dial to produce those numbers?
Basically the angular position. So
the dial actually moving around on the front?
yeah, it's like normally when you're dialing this lock around, you have the numbers and you have an index to dial to. So I'm just using the numbers as a reference point for myself. Like for example, the contact point on that one, the one I'm using, the right contact point is something like 13. But if I get the one on the graph showing 85, if I get that in position and go to my contact points, I'm reading 12.5 on the dial. So I'm using the lock itself as a measuring tool. I don't know how correct it is. I just know it's more correct, and I can use that to my advantage, that know that that might be the correct number, or it's at least giving me the next step to be on and to continue from. Yes?
Your graph showed 1 point. Are you measuring just one contact point or the distance between the two contact points?
Technically, it would be best to measure both contact points, like left and right. But because if you look at the lock, it was showing on the pictures that didn't show up, the cutout shape in the cam wheel is, on the one side it's almost vertical, on the other side it's sloped. So you're measuring the sloped surface, which is the right contact point. Because if you get any movement, so the fence goes deeper into the cam, of course it moves less than when it's more up. So if you have a sloped surface, you can actually measure differences in the readings. But with a vertical surface, like on the left contact point, you get almost no reading differences, no matter how far along with the manipulation you are. So sometimes you need to read them both, sometimes not. Most of the time you only need the right contact point and that's it.
Thank you.
Okay. There.
So you're talking about wear on the wheels. Have you found in your experience that that makes a particular like a significant difference to this, or
yes,
effectively the same as all locks?
Yeah, wear on the wheels or wear on the lock parts. It's a battle when you're actually opening real-world safes that have been in use for a few years. The wheels wear, like they get sloppier. They might not stop at all. When you dial fast and you stop, the wheels continue turning. Or the worst case scenario is that the part that locks the wheel is actually two parts. There's the inner part and the outer part. And when you change the combination, it disconnects those parts, and you can turn the other one without affecting the other. So you change the combination with that, and you lock it again. If the locking mechanism doesn't work or is somehow not locked, the inner part of the wheel turns, but the outer part doesn't. So you're in a lot of trouble when dialing it. You're just driving the parts with little friction in between, so you have to go really slow. Other part is, for example, in the lock you can see a little flag in the middle. It's a little key that connects the dial axis with the cam wheel, and that can get a little sloppy also. So there's a little problem that you have parts that are not properly connected. And finally, if you have a lot of wear on those wheels itself, it shows up in the measurements, like you can actually get easier measurements, or when you're measuring with an electronic tool like this, you get more consistent readings because the wheel has worn down, like all those little high peaks from the manufacturing doesn't show up anymore. So it makes it easier in that sense.
Just in regards to false gates and what we've got, we still use the same technique for stuff involving false gates?
So you're basically asking if you have false gates on the wheels, does it affect the process? Basically, it makes it more difficult, but eventually you're just finding more lower spots from the wheel. Like you start recognizing that you found a false gate, so you know to look for the real gate after that. So you might first get some number correct and some numbers into the false gates. And when you discover that you didn't open the lock yet, you know that there's false gates and you have to just keep looking more. So it's actually an advantage point. In some locks, like the S&G has one model that has false gates, 2 false gates per wheel, equally spaced. So if you find one, you find one gate or false gate, you know to check 120 degrees from that and 120 from that, and you know that those are 3 only possible combinations for that wheel. So it's an actual shortcut. It's only a problem when you start the manipulation, but once you find one of them on each wheel, the game is over. Yeah?
That attack that you're outlining there, how would that work with like an 8500 as opposed to?
I haven't dialed 8500 series ever. I know it's the manipulation proof lock that you have to push or turn the knob or whatever after dialing, but I haven't tested it, and those usually are the kind of locks that are not giving you contact points at all. It's basically a hook up a robot and go for it.
I wasn't sure if the mechanical aid that you developed was able to pick up something that you couldn't physically feel by.
Would require testing. I'm not saying yes or no. I'm saying maybe or maybe not, because I would need the lock to fiddle with, and because I'm a poor machinist, I don't have money to buy them. So if you have locks, I'm very open. I have a 23 kilogram limit on my suitcase. Yes. Yeah.
Is the main manufacturing defect with the wheel the centering, and so you always get those sinusoidal shapes? Is that what you expected?
Basically, yeah. I'm not exactly 100% sure on this, of where does that concentricity error come from. I suspect that it's because there's two parts, the inner and outer wheel, and there's basically springy parts pushing them together, so it pushes it off center. Because of course, because they rotate to each other, there has to be a gap between them, and it just pushes the other part out.
But when you plot the contact points, you always get the sinusoidal shape if you just measured one wheel.
Yeah, basically. That's about it. If you have anything else, go tuck me from the sleeve later after buying a beer. Anyway, thank you.